Hello students, so this is the continuation of lecture 3, unit 1. Today we are going to discuss about demodulation or detection of DSBSC AM. So demodulation or detection can take place by two different methods. One is synchronous or coherent detector, second one is Castas PLL detector. Synchronous or coherent detector. So coherent detector uses exact carrier synchronization for retrieving the message signal from modulated signal. These types of detectors are mainly used for detecting double sideband suppressed carrier and single sideband suppressed carrier signals. It consists of a product modulator with a low pass filter. For detecting a signal, a local oscillator at the receiver end is required. The frequency and phase of the locally generated carrier and the transmitter carrier must be synchronized, that is exactly coherent. All types of linear modulation can be detected by using synchronous detector or a demodulator. It consists of a product modulator with the low pass filter. So this is a block diagram of any coherent detector. It may be applicable for DSBSC and SSB signals. So the incoming signal is first multiplied with the locally generated carrier and then passed through a low pass filter. The filter bandwidth is same as the message bandwidth omega m. The local oscillator should be exactly synchronized with the carrier signal in both phase as well as velocity. The coherent detection or coherent detector or synchronization can be achieved in another way also. Here the carrier signal is directly obtained in the receiver side, or we can derive the carrier in the receiver side by retrieving a special circuit with special circuit. So in the two ways we can achieve synchronization. So here we follow direct apply method, that is you are directly giving a carrier signal at the receiver end also. Whichever you are used in your transmitter side, that the same carrier is applied in the receiver also. So in this case, consider E1 of t is equal to Em Ec sin omega t sin omega Ct. Second signal Et is Em sin omega Ct. The output of the nonlinear device which acts as a multiplying device is given by E of t is equal to product of these two signals. So E of t is equal to Em Ec E sin omega mt 1 minus cos 2 omega Ct. After passing through the low pass filter, the second order harmonics in the above equation is eliminated. So we will get only Em Ec sin omega mt. Assume that the local oscillator carrier to have a phase difference with the transmitted carrier, then the carrier is represented by E2 of t, E sin omega Ct plus phi. This phi represents the carrier phase difference. The output of the nonlinear device is given by E of t is equal to multiplying this E1 of t and E2 of t. So Em Ec sin omega mt sin omega Ct sin omega Ct plus phi. So when you multiply those equations, we will get the simplified expression like this. So here after passing through this content to the low pass filter, the second order harmonics terms is eliminated. Even the DC components are eliminated. So the remaining terms will be E of t is equal to Em Ec E sin omega mt cos phi divided by 2. So if the value of phase, that is the phase difference, is 0, then E of t is Em sin omega mt, because cos 0 is 1. If the phi value is equivalent to 90 degree, then it will be a minimum value, because cos of 90 is 0. So the entire thing will be eliminated. So the demodulated signal V0 of t is therefore proportional to the message signal when the phase error phi is equal to 0, and it is minimum, that is 0 level, when phi is equal to plus or minus pi by 2. Thus the phase error phi is in the local oscillator causes the detector output to attenuated by a factor equal to cos phi. As long as the phase error is constant, the detector provides a undistorted version of original baseband signal. This is one method of retrieving the DSB signal. The second method is Costa's PLL detector. So this is the block diagram of Costa's PLL detector. Here also we are going to obtain the modulating signal from DSP signal. So product modulator, one 90-degree phase shifter is placed in the transmitter side. Along with that, one low pass filter, voltage control oscillator, and we have phase discriminator in this block diagram. So the Costa's receiver is one of the method for obtaining the practical synchronous receiver suitable for demodulating DSBSC waves. When compared with coherent detector, we will go with Costa's PLL detector. It consists of two coherent detectors. One is the upper half, second one is the lower half. Same input signal and transmitted carrier. This detector is known as in-phase coherent detector, I channel, and the lower half is quadrature coherent detector or Q channel. These two detectors are coupled together to form a negative feedback system designed in such a way that to maintain the local oscillator synchronous with the carrier wave. Operation of the circuit. In this case, the I channel, let us assume this is I channel, this is Q channel, because 90-degree phase shift is applied in this second half cycle, second half of the circuit. So in this case, I channel output contains the desired demodulated signal, whereas Q channel output is 0 due to the quadrature null effect of Q channel, because these two are out of phase with each other. So if we want the desired signal in the upper half, automatically the second half signal is get eliminated. Similarly, if you want the desired signal from the Q channel, automatically the upper half cycle circuit is eliminated. The phase discriminator provides a DC control signal which may use to correlate local oscillator phase error. The local oscillator is a voltage controlled oscillator. Its frequency can be adjusted by an error control DC signal. The Costa's receiver ceases phase control when there is no modulation, and that phase lock has to be re-established with reappearance of modulation. Thank you.